top area over the high latitude, which the rainfall can be more, and then to certain location that our product is like overestimated, but after correction we make it more smaller. But of course, here I use the same example, use our state for radar estimates over the United States for comparison. So that you can see the right hand side is the original.
We lost the PowerPoint again.
Yeah, so there is okay. So here is the image view. So you got the view right now.
Yes,
right?
Yes, we got it.
Okay, good. The right hand side image is the estimate from our system, and the radar observation for that particular day is over the left hand side. Only show the region of effective radar coverage. And then here is the GPCB and press microwave corrected product. And then there is more process to the radar estimate. For our estimate, for our evaluation, the day-by-day estimates are much improved according to this process, and which extend we plan to extend all the estimation to the past 30 years. So that would be very useful for kind of study. Okay, here is the highlight area. Now let's move to another topic. So the part right now, we want to improve our estimate, and hopefully that local gauge information can be very useful. So we can use the local gauge information to improve our study and to our algorithm estimate. And I put the case study over Chile here as an example. So here, this is the coverage of our study.
Sorry, we lost PowerPoint.
No,
I will lift the paper so that when we lost the PowerPoint, if you see I'm lifting the paper, can you put the PowerPoint on?
Okay. Yeah, because here we still see the PowerPoint continue, but we don't know that your link is lost. So you just give us a reminder.
So
can
you see a piece of paper from me?
No, actually we have the PowerPoint view.
Oh, I see. So you have the PowerPoint view. I see. So I will.
Right, but somehow the connection to you is connected, but we don't know. So you have to give us a sign.
So Professor Su, before we continue, do you see a little box on your right?
No, we
right
see nothing. We only see our PowerPoint in the full screen mode.
Yeah. So there's a little box on the bottom right corner with the stop. So try not to move your mouse over that. Yeah, that one. Do not click on that one.
Okay. We never.
I see. So maybe that's a technical problem. Okay, thank you. So you may continue. Thank you.
All right, sure. So the study areas I put it over here. That is the Chile, and which has a really big the latitude coverage over like 40 degrees, and longitude coverage is like 10 degrees around. So you can see that. And the gauge, it has covered for 456 gauge over this study area. And the study period is from 2009 to 2013 for 5 years under this type of experiments. And observation is over here. You can see rainfall distribution to the south is much heavier, much higher, to up to 2,500 kind of level. And to the north is very low, even just couple hundred kind of distribution, so that you can see huge variabilities of rainfall over just this particular region. Of course, extend extended to a larger latitude differences. And our data set also collected to the same time period for this experiments. And here we put it into different time zone in the every 2 degrees, so that it has like a 14 2-degree boxes or something. Then we can evaluate the result according to the regions. So now, start from the gauge data and the distribution estimation, then we put it into every 1 degree by 1 degree is one particular separate.
Professor, so we lost the screen.
Lost again, yeah. That's right.
Can you see us?
We can see you now, but
Okay. Yeah.
when you
I think
say
sometimes you need to say hello or something, and then continue.
Sure. Okay. So now we start with every particular 1 degree, 1 by 1 degree is a separate estimation, box. So you can see all the region is separated into a number of boxes. Then gauge inside the box are assumed, assumed to be the same distribution, so that we're gonna calculate distribution, rainfall distribution over 1 degree by 1 degree box. And of course, here has like 98 boxes, so that there will be 98 separate rainfall distribution. And then the bias correction from our data using gauge data is done in this way. So we collect the concurrent samples from our estimates and also gauge estimate. And the collection is using 0.04 degree by 0.04 degree as a reference grid, so that the gauge is located in that particular 0.04 by 0.04 degree, then they consider as the sample in the same time and concurrently they are shown up in the same time, so that it will be collected. And then it's 1 degree by 1 degree box. All the 1 degree by 1 degree box, and then they have their collected samples from both PERSIANN-CCS is our estimate, and also the gauge estimates. And then we calculate the cumulative density function for those data sets, which I will explain more in the next few pages. And then, of course, there's one particular situation, which is you might see some of the boxes which has no gauge over those boxes. And for those 1 degree by 1 degree box without gauge inside, then we have to use the gauge from the neighborhood boxes to support the estimation of the so-called cumulative distribution function for that particular box, which I will tell you more about that. So they are in couple stages for this kind of process. The first step is the estimation is in this case it is in the daily scale, so that we're gonna collect the daily rainfall. And one important notion here is that the daily rainfall collection has to match to the daily gauge rainfall. So basically, our data set is available every 30 minutes or an hour. So that, and local gauge daily rainfall, it has a potentially different time, which is maybe to the local time. From some area, maybe from 8 o'clock in the morning to the next day, 8 o'clock in the morning local time. But then, to the daily total rainfall, we have to adjust our rainfall, daily rainfall to local time daily rainfall in the same time scale, so that it can pair with the same time for the analysis. So this is first step. And then the second step is we're gonna match distribution from ours estimates to the gauge estimation. So the concept is just like this. I put it for say 1 degree by 1 degree box, so we have collect a lot of samples. And the green one as you can see in the left-hand side, is the probability distribution of our estimates. So that you see the green curve, and then gauge has its distribution. Okay, the x-axis is rainfall rate, and y-axis is probability of the rain rate at that particular area after you collected the data set. So now the concept is well, the distribution for our estimates and gauge are not together. So our intention is we're gonna move the green line, green curve, to the yellow curve or orange curve. Okay. So in that, to do this, we actually do that over the accumulated distribution, so that we do accumulation of probability function, so that you have, instead of PDF, now you get a CDF to the bottom panel here. So the CDF from satellite estimate is CCS, and CDF from gauge estimate is over the other side, over the yellow. So we now our purpose will be shifting the accumulation curve from the green to the yellow. And if we move the green curve to the yellow, which is in accumulation, then we take the differential back into the PDF, which would imply that the PDF for the green now move to the yellow. So that we all do it over the accumulation curve here. So for the mapping of the CCS to the gauge, which will start from here, and looking at the same probability, contact probability, and then that will be a point of reference. Of course, in a different context, then they have different reference values. So as a result, there will be a mapping from the CDF curve that CCS can map into the rain gauge rainfall. So this is the process in general. And then I give you a little bit more detail for the next page. So now we will come back into the 1 degree by 1 degree box, and it has 25 by 25 0.04 degree by 0.04 degree boxes over this 1 degree by 1 degree box. And here 0.04 by 0.04 is the CCS grid estimate I put it here. And then gauges are split somewhere all around. So gauge observations are put in over the distributions over the region. So we now collect the samples with a concurrent sample of 0.04 degree CCS grid with gauge. So those samples are collected out over this particular 1 degree by 1 degree box area. So in that, then we have a lot of samples which over 5 years, and the estimation is separate season by season. So each season we do have one particular distribution for that. So in that we have the distribution. So now we start to calculate the accumulated probability distribution, so that you can see rainfall rate and from the satellites and put it into the blue one, and then rainfall rate accumulated curve from gauge is in the red one. So now our purpose will be, from different kind of contacts, the satellite image estimates would map into the estimate of gauge, which is our adjusted estimate for the satellite. So that is pretty much the concept to do that. And by the time of November, then we have more detail for this, and but in the same time for the code for implementation of the ideas. And now coming back to the curves here, we see the gauge over the left-hand side, and the 1 degree by 1 degree box coverage over the right-hand side now, the 98 boxes. And then you can see the parts with the thin line means gauges are available, but with the solid boxes, heavy boxes, in the point 1 degree by 1 degree here, they are no gauges available. So we have to take care of those parts without gauge available for the distribution curve data. One by one we do that, and so I put a green box for just the parts which gauge available. Then we have a gauge curve, and then we also have the satellite estimate as a CDF curve for that. And all of the thin line 1 degree by 1 degree boxes should be available for the curve like this. And then for the box, I put it here. This is the red box here without gauge available. What we do is we extend the coverage to a much bigger area to collect the concurrent samples from the gauge to support the box. So that you can see in this case, we have 3 by 3 enlarged for the coverage, but of course the concurrent sample is put in together for that particular 1 degree by 1 degree box for the CDF curve. So in that we do have the CDF curves, and then we can have that as a mapping function for how to map our CCS estimate to the gauge estimate. And the final stage is we need to take care of the data smooth over the boundary. For example, this is okay. Here is 4 boxes of 1 degree by 1 degree. If I have a estimate cross over the border, then the estimate over the left-hand side has one particular transfer function, and then over the right-hand side has another transfer function. So that it probably potentially have a discontinuity over the border. So in order to solve these problems, that estimation for a grid box is now using 4 neighbors 1 degree by 1 degree box for the smoothing over the border and over the pixel. For example, the blue we put here, and they are 4